welcome to this next set of lectures for the topic of scalars, vectors and tensors. So, in the previous couple of lectures, what we saw is that we reviewed the definitions of what is scalars and what is vectors, and we gave a most general set of definitions using which we can also include more complicated objects such as tensors. Today and the next lecture, the plan of this couple of lecture is to now apply these concepts to do some calculations with vectors. Now, when I say calculations, what I am going to review are these elementary algebraic operations. So, namely the addition, and then we will talk about the products or multiplications between vectors. Now, what about subtraction? So, we will see that subtracting two vector is nothing but adding one vector to the opposite of the second vector. So, this is included in the operation of addition. What about division? So, this is a remark that there is no meaning of the operation of division between two vectors, because you cannot divide direction with another direction. So, division is an illegal operation. So, for vectors we will see that there are additions and multiplications or products, and within product we will see that there are different kinds of products we can define for vectors, and we will go through one by one. So, before we go to the actual calculations, so we need the concept of unit vectors. So, we are quickly going to review this concept. So, unit vector is basically mean a vector with whose magnitude is 1. So, unit means 1. So, unit vector is a vector whose magnitude is 1. So, let us take an example. So, for example, if I take this coordinate system, so I have drawn a Cartesian coordinate system. So, this is the origin, this is the x, y and z axis. Now, I want to specify the direction or orientation of this axis. So, I have drawn a vector, this arrow represents this vector. So, this vector, the length of this vector is 1 unit. So, if x represents length, then it could be 1 meter or 1 centimeter. What is the appropriate unit for the problem? If the x represents force, then it could be 1 Newton, 1 micronewton and so on. So, this is 1 unit for the time being, we assume, and the direction of this vector represents the direction of the x axis. So, this symbol, note the symbol. So, this symbol is a little hat, it is called hat or caret. So, this denotes the unit vector. So, in general the convention is we represents an arrow represents a vector which can have any magnitude, and this hat represents a unit vector whose magnitude is 1. So, now let us take a vector A which is along any direction. So, this is our vector A. Then what is the unit vector along A? The unit vector along A is a vector whose magnitude is 1 and its direction is same as the direction of A. So, this represents the direction of A. So, as we seen in the previous set of lectures, that we can write the A as a sum vector addition over 3 little pieces, one along x axis, one along y axis, another along z axis, and these Ax, Ay, Az represents the corresponding components along x, y and z direction. Then the magnitude of the vector is given by this formula. So, if you know the component of the vectors x, y, and az, then it is a simple application of Pythagoras rule that the magnitude of the vector, that is the distance between the origin and the so distance between the tail of the vector and the head of the vector is given by ax square plus ay square plus az square. So, here the tail of the vector is situated at the origin. Then if I now divide the vector by its magnitude. So, remember that the magnitude is a magnitude, it is a real number, and I am assuming that it is not 0. So, we can, so by real number I mean this is a scalar. So, remember the definition of scalar. So, this magnitude of the vector does not change if I do a coordinate transformation or rotation as we took in the last class. So, if I divide by magnitude, then the vector that we got, which is called the unit vector, will have a magnitude 1. Now, I want to point out highlight one important fact, for which we will take a couple of example in 2D. So, let us say that in 2D we first draw, suppose we take a particle which is moving along a straight line, which means the direction is not changing, is constant. So, then if we represent a unit vector, so suppose this is my x axis, then we represents the unit vector by x hat. So, its magnitude is 1 and its direction constant. So, we can similarly draw another unit vector along the y axis, whose magnitude will be 1 and the direction will be constant. So, this is like a particle which is moving in a straight line. But in general, the direction of the unit vector need not be constant. For example, consider a circle and consider a particle is moving along circle, or a person is walking along, let us say the circular path. So, in this case we can represent the direction in which the person is moving. So, let us say you take the center of the circle as origin, and this is my x axis, this is my y axis, and let us say this is the location, okay, let us say this is the location of the person at some point of time. Then this is the vector OP, represents the position of the person at some point of time p. Then this tangential direction is the direction along which the person is moving. It represents the direction of or the velocity of the person. So, this tangential direction we can denote a unit vector whose magnitude is 1 and which direction represents the tangent direction at any point of time where the person is located. So, this is usually denoted by the symbol theta, and this theta hat represents the unit vector along the tangential direction. So, the magnitude of theta hat is 1, but the direction is not constant, it is continuously changing. So, when we say unit vector, it does not mean that anything about the direction, only the magnitude is 1. So, now we are going to work through a series of examples to illustrate the different elementary vector operations, the additions and the products. So, this is our first example. So, we have a two vectors, if A is 10x minus 4y plus 6z and B is 2x plus y, find component of A along y magnitude of 3a minus b, a unit vector along a plus 2b. So, this is the problem. So, let us work out one by one. So, the two vectors a and b are given and they are given in terms of the components. So, we can write, so just by the information that is given. So, 10 represents the component along x direction, minus 4 represents the component along y direction and 6 represents the component along z direction. So, accordingly the answer is minus 4. So, minus 4 is the component of A along y direction. Here x, y and z, these are the unit vectors along the coordinate axis. Next part. So, next part we have to calculate the magnitude of 3a minus b. So, let us do it step by step. So, a is given. So, first is what is 3a? So, 3 is just a number, it is a scalar. So, we multiply a scalar with a vector with a scalar, it does not change the direction of the vector, it just changes the magnitude. So, 3 times a is 3 times 10 x hat minus 4 y hat plus 6 z hat. So, this is 30 x hat minus 12 y hat plus 18 z hat. Now, minus b. So, you can think of minus b as multiplying b with a minus 1. So, if this represents b, so the length of the b is the length of the arrow is the magnitude of b and the direction of the arrow represents the direction of b, then minus b is an arrow in the opposite direction. So, the length remains same, but the direction is opposite. So, then minus b is minus 2 x hat minus y hat and there is no, note that there is no z component for minus b. So, if I add them, then 3a minus b is 28 x hat minus 13 y hat plus 18 z hat. So, then if I apply the formula, so then the magnitude is given by the square of the components and then take the square root. So, 28 square is 784, (13) square is 169 and 18 square is 324. So, this will turns out to be some value. Okay. Next question. What is an unit vector along a plus 2b? So, okay. So, first we need to calculate the vector a plus 2b. So, we write down the vector a and then we write down the vector 2b, which is 2 times b. So, 4x plus 2y hat. So, then a plus 2b is given by 14 x hat minus 2 y hat plus 6 z hat. So, now to calculate the unit vector. So, a unit vector along a plus 2b is a vector which has the same direction as a plus 2b. So, we have found the vector which is a plus 2b. Now, if I divide it by the magnitude of a plus 2b, that represents the unit vector along a plus 2b. So, we need to find the magnitude. So, the magnitude is 14 square plus minus 2 square plus 6 square. So, the magnitude by definition is always positive. So, we always take the positive square root. So, this is 14 square is 196 plus 4 plus 36, which is square root of 236. So, then the the magnitude of this vector is 10 divided by square root of 236 x hat, sorry, I am sorry. So, this is a plus 2b. So, this must be 14 minus 2 divided by 236 y hat plus 6 divided by 236 into z hat. You can verify that if you apply the magnitude of this vector on the right hand side is 1. The next example is points P and Q are located at, so the coordinates of 2 points are given. Calculate the distance vector from the point P to Q, the distance between P and Q, and a vector which is parallel to PQ with magnitude 10. Okay, let us do it one by one. So, here is an important remark. So, when you do physics problem and vector analysis problem in particular, you don't just apply the formula, don't start by thinking what is the right formula to apply, start by drawing pictures that sort of gives you a good understanding of what is there in the problem, and it helps you to avoid mistakes in the calculation. So, let us try to draw the location of this point P. So, we have this, suppose this is my x axis, this is my origin, this is x axis, this is y axis and z axis. So, it says that the x component is 0. So, x component is 0, y component of point P is 2. So, let us say I go 2 step along y direction and then the z component is 4, that means I need to go 4 step along z direction. So, this point P is located in the yz plane. So, this is point P, and if this is my origin. So, OP represents the position vector or location vector of point P. Similarly, so minus 3, so that is on the other side inside the screen, and 1. So, you have to go 1 step along the y direction and then 5 step along the z direction. So, point Q will be located somewhere in here. So, this is in, remember this is in 3D plane. So, something like this. So, then from P to Q, this vector represents a vector from the distance vector from P to Q. Now, if I look at this picture, I can see that this PQ is, by applying the laws of vector addition, is OQ minus OP. So, OQ is given by the position vector of Q, which is minus 3 x hat plus y hat plus 5 z hat. So, this comes from here minus. So, we have 2 y hat plus 4 z hat. Now, if I take the difference, then I get minus 3 x hat. So, plus 1 minus 2 minus y hat and plus 5 minus 4 plus z hat. So, this is a distance vector from P to Q. So, now I need to know the distance between P and Q. So, the distance between P and Q is the magnitude of this distance vector. So, let me remember what was the answer. So, minus 3 x hat minus y hat plus z hat. So, this is magnitude of minus 3 minus 1 minus 3 x hat minus y hat plus z hat. Let me check it. So, minus 3 x hat minus y hat plus z hat, minus 3 x hat minus y hat plus z hat. the magnitude of this vector. So, which is given by square root of minus 3 square plus minus 1 square plus 1 square, which is given by, so 9 plus 1 plus 1 square root of 11. So, a unit vector, so this is the distance. So, this is the magnitude. So, this is the distance, the scalar distance between P and Q. Now, we want a vector which is parallel to P Q with magnitude 10. So, now I want a vector A. So, A has a magnitude 10. So, mod A is 10 and the direction of A, so this means that if I so A is a vector. So, if I, so the direction of the P Q can be represented by an unit vector along P Q. So, then the problem means that A is a vector whose magnitude is 10 and direction is along the direction of P Q represented by the unit vector along P Q. So, let us calculate the unit vector along P Q. So, P Q is given by, so minus 3 minus 1 plus 1. So, minus 3 x hat minus y hat plus z hat, and the magnitude was square root of 11. So, the unit vector is minus 3 by square root of 11 x hat minus 1 by square root of 11 y hat and plus 1 by square root of 11 z hat. So, then the answer is the A is a vector which is so this is the answer. You can again verify that the magnitude of this vector is 10. Our third example, so forces F1 to F6, so there are 6 forces acting on an object P. So, this is an object P and on this object P there are 6 forces. So, this is F1, this is F2, this is F3, F4, F5 and F6. So, what is the total or the resultant force acting on P? So, that means there are 6 forces, we have to find the sum of these 6 forces F1, F2, F3, F4, F5, F6. This is the easiest way since the components are not given. So, the only way you can do it is by applying the vector law of addition to these pieces of so think of this each force as a little piece of arrow and then you start from anywhere. So, take the first force for example and then you take the second force, put it in the at the head of F1 and then you join the F3, the third force at the head of F2 and so on as shown in this figure. And then finally, if you, so when you join these forces, remember that you are not changing the direction of the forces and you are not changing the magnitude, that is the length of this arrow. So, all you are allowed to do is to sort of slide these arrows parallel to itself and then you get the, this is the tip of the last force which is F6 and this is the head of the first force which is F1. So, now if you join these two points, that will give you the resultant force or the total force which is R. So, note here that the notation, so here I represents the forces by a bold font instead of an arrow. So, the bold font means it is a force is a vector. So, in this case the main lesson or main point to remember in this problem is that the order in which we add the forces is immaterial. So, here I have added F1 then F2 plus F3 plus F4 and F6, but you can switch the order, you can add F2 to F3 and then F6 and then F5. So, in any order you can. So, when you do a vector addition, the order in which you add the vectors does not matter. So, next we go to the multiplication of vectors, or sometimes called products of vectors. Now, we will discuss three kinds of products in this lecture, set of this and the subsequent lectures. So, the first product is called dot product. Now, so what we are doing here is that we have two vectors, and if you have two vectors and by combining these two vectors, what is the resultant combination? So, we will see that there are two possible combinations. So, many different kinds of combination is possible. So, the dot product is a operation or a rule which you apply on two vectors, and the result is a scalar. So, you make a scalar out of two vectors. So, this is dot product. So, suppose you have two vectors A and B. So, let us say we write the A in the Cartesian components. So, this is its components along x, y and z directions are x, a, y and a z. So, A will be a x times unit vector along x, a y times unit vector along y plus a z times unit vector along z. So, these are vector additions. And similarly for B. Now, the symbol A without the arrow represents the magnitude of A, and similarly for symbol B. So, with arrow represents the vector, without arrow represents the magnitude. Then A dot B and theta is the angle between A and B. Then A dot B, so this is the notation for a dot product in the middle. So, A dot B is defined as the magnitude of A times magnitude of B times the cosine of the angle between A and B. That is the rule, and we can write the same product directly in terms of components. So, it is x component times x component plus y component times y component plus z component times z component. So, this is the rule. Now, in this course, some quantities that are dot products will be work done and power. So, we will discuss those quantities in appropriate places. Here we focus on the mathematics. Now, here is my second point. So, when you apply or when you come across any formula, mathematical formula, we just before do not simply try to remember the formula by force. First try to ask yourself, does it make sense? This is a very important question that helps you understanding physics. And what are the strategy? So, the first strategy is the draw sketches. As you know that there is a saying that a picture is worth of 1000 words. So, drawing pictures helps you understand the concept. So, what is the dot product means in pictures? Suppose this is my vector A. So, this is the length of this arrow represents the magnitude A, and the direction of the arrow is the magnitude. And suppose this is the vector B, and theta is the angle between the two vectors. Note that there are two angles possible, and by convention we usually take the smaller angle as the angle between two vectors. Now, you drop a perpendicular from B on A, then you see that this piece represents B cos theta. So, then the A dot B is nothing but this B cos theta is sort of the contribution of B in the direction of A. So, this is called the projection of B in direction of A. So, then this A dot B is a number, first of all it is a scalar. If you do a coordinate transformation, it remains invariant. So, it is a scalar, it is a single number, it is only magnitude, no direction, and this represents the projection of B in the direction of A times A. So, this is kind of you are multiplying A, the magnitude of A, by the projection of B along A. But you can also do the opposite. So, for example, again the same picture. So, this is our B, this is the same angle theta. Now, you drop a perpendicular from A to B, and then you can see that this represents A cos theta. So, then the same thing you can write it as A cos theta times B, same dot product. So, then it will represents the projection of A along B times B. So, this is the pictorial meaning of dot product. So, the next strategy, again, does it make sense? The next strategy is to consider special cases of the formula. So, in this formula A and B, sort of any general vector A and B, that does not give you any good picture. So, let us take some special case. So, let us take the unit vectors. So, these are easy case because the magnitude is 1. So, first let us take, for example, for simplicity I am going to take the Cartesian components, Cartesian unit vectors. Suppose this is my origin and I am choosing a Cartesian coordinate system to denote these vectors. So, what is x hat dot x hat? So, by if I apply this formula, then the x hat magnitude is 1, x hat magnitude is again 1, and cos theta, that theta the angle between a vector with itself is 0. So, this is cos of 0 is 1. So, this gives you 1, and similarly for the other components. Now, if you take two different unit vectors x dot y hat for example. So, this angle theta is pi by 2 or 90 degree. Then if I apply the same rule, so the magnitude of x hat is 1, magnitude of y hat is 1, and the angle between them is pi by 2 cos pi by 2, which is 0. So, that means that there is no x hat does not have any projection on y direction, and similar vice versa, that is y direction does not have any projection on x direction. So, that is why, so they are perpendicular. So, if you take two perpendicular vectors, then their dot product is 0. Now, we can apply this concept of product to verify the to calculate or to define the components of a vector. So, suppose I take a vector A, which is a x times x hat plus a y times y hat plus a z times z hat. Now, let us calculate the dot product between this vector times the unit vector along x direction. So, this is a x x hat plus y y hat plus a z z hat dot x hat. Now, from the previous calculation, so x dot x is 1, so you will get a x, and y dot x is 0 and z dot x is 0. So, you just get a x. So, a x then represents the projection of A along x direction, and similarly a y and a z. So, this gives you a pictorial meaning of what is the meaning of the components of a vector. So, let us take an example. So, two vectors are given A and B, find the angle between A and B. So, how to find the angle? So, if I apply this definition of the product, so this gives you A times B times cos theta, and again I can write the same thing in terms of the components. So, A x B x plus A y by plus az bz. From the given problem ax, ay etc. are given. So, I can calculate this quantity. From the components I can calculate also the magnitude of the vectors and the magnitude of vector b. So, hence we can get the from writing the dot product formula in two different ways and equating them, we can compute the angle. So, let us proceed. So, first the magnitude of A, which is 3 square plus 4 square plus 1 square, which is so 9 plus 16 square root of 26. Magnitude of B, which is again, so note that there is no y component, x component. So, this is 0 square plus 2 square plus minus 5 square, which is square root of 29. Now, if I calculate the dot product directly from product, I get 3 times 0 plus 4 times 2 plus 1 times minus 5, which is equal to 3. So, then I get that 26 times 29 times cos theta gives you 3. So, then you can solve this equation to get cos theta to be 26 times 29. Now, note one thing, that as you know that if you know the cos theta and then you are solving cos theta to calculate theta, there are two angles which has the same value of theta. So, an angle, so cos of a theta is equal to cos of 2 pi minus theta. So, in general you will get two solutions, one which is theta and one which is 2 pi minus theta. So, by convention take the smaller angle, and that is the angle between by convention the vectors a and b. So, we will continue this lecture, this calculation. So, we will take more examples in the coming lectures. Thank you.